In this video, we're going to have a quick look at how sounds can be stored using binary numbers. And if you haven't already, make sure that you've watched the videos or at least got yourself confident on how images are stored using binary numbers and how numbers are stored using binary. Because if you get those two ideas, this one should be pretty straightforward. So, let's start off with a sound wave. Now you might have seen a sound wave before, and if you haven't, you can open any sound file in a program like Audacity, which is free, and it'll show you what the sound wave looks like. You can even zoom in and you'll be able to see what I'm doing here in much more detail. Now, this sound wave here looks an awful lot like a graph, and it works like a graph, and that's really helpful because we've got the x-axis, which represents time, and we've got the y-axis, which represents amplitude. Okay, so if we look at the amplitude of this, it's kind of the height of the wave. And what we can do then is we can take samples from this at key points. In fact, not just at key points, we can take these samples at fixed intervals. So if we look here and here and here, it's not drawn very well, but those there should be fixed intervals, so they're always the same gap in time. So we take these samples at fixed intervals, and that idea is very, very, very important. That wording is very important when you come to answer exam questions. So, what do? We stick a microphone out there and we record the sound, and the microphone listens into the sound, and the computer device takes samples of the sound, it measures the amplitude at fixed intervals, and then each of these values we write down as a binary number. And once we have those binary numbers, we can recreate the graph. And if we can recreate the graph, then we can recreate the sound file. And we can reproduce the sound using some speakers. And that really is all there is to it. So, we record a sound with a microphone, and what we're actually doing is measuring the amplitude of the sound at fixed intervals, and then writing down each sample, each value, as a binary number. And we save that to a file, and we're done. When we need to, we can reproduce the sound from those binary numbers. And that is how we store, how we record sound and write it down using ones and zeros so we can save it on a computer system. Now there are two issues around this that we need to be aware of. And the first one is the size of those fixed intervals. And the size of those fixed intervals is known as the sample rate. So I'm just going to make some space on this whiteboard so we can make a few notes on key phrases that we need to know. So the sample rate is how frequently we record those samples. And it's measured in hertz because it's the number of samples per second. A typical sample rate for a piece of music might be 48 kilohertz. And you can, when you're recording, change this sample rate and see what it does. If we double the sample rate to 96 kilohertz, then the sound is going to sound more accurate and the file size is going to go up because we've got more samples to store. If we go the other way and we reduce the sample rate to say 8 kilohertz, then we have the opposite effect. We have less accuracy in the sound, but the file size is a lot smaller. Now, for high quality music, you want the highest quality sound possible. So this is the accuracy. And again, that word is really important. As the sample rate increases, we get more accurate representations of the sound, but we also get a bigger file size because we're having to write down more samples per second. If we go the other way, we have less accuracy and a smaller file. This is perfectly decent for things like Skype and mobile phone calls. This is more what we want for high quality audio. And that's the most well-known factor that's going to affect the quality of your sound file. The other one is the bit depth. And bit depth works in almost exactly the same way as colour depth does in binary images. So if you think of that graph again, which I'll scribble down here again very quickly, that waveform, and we want to write down this value here, well, if we've only got 2 bits per sample, then we only have 4 possible values that we could write down. That one there, that one there, that one there, or that one there. Okay, so 1, 1, 1001000. So we've only got those 4 possible values to go from, so we pick the closest one. It's not very accurate. Whereas if we have 8 bits or 16 bits per sample, we can be much more accurate with how high up or down this graph we are, and our sample has a much more accurate value. So in the same way that with colour depth, if you have 16 million possible colours to choose from, you can get the exact shade just right. With digital sound, with a higher bit depth and more bits per sample, you can get the exact value for the amplitude really, really accurate. If you have a much smaller bit depth, it's much harder to get that recording to be accurate. So these are the 2 factors that will impact on the accuracy of your sound and the file size of your sound. And in ideal conditions, for the best possible sound, you want the highest sample rate, more samples per second, and the highest bit depth, more bits per sample. So you get the highest quality sound overall. But if you need to email it, stream it, send it over the internet, or just reduce the amount of data stored on your hard drive, then you might need to lower the sample rate or lower the bit rate. And that's digital sound.